on convergence of regret minimizing strategies to Nash equilibrium in routing games. As mentioned earlier, one Nash setting for regret minimizing algorithms is online routing. For example, a person could use such algorithms to select which of n available routes to use to drive to work each morning in such a way that his performance will be nearly as good as the best fixed route in a hindsight, even if traffic changes arbitrarily from day to day. In fact, even though in a graph G, the number of paths n between two nodes may be exponential in the size of G, there are a number of external regret minimizing algorithms whose running time and regret paths are polynomial in the graph size. Moreover, a number of extensions have shown how these algorithms can be applied even to the partial information setting, where only the cost of the path traversed is revealed to the algorithms. In this section, we consider the game theoretical properties of such algorithms in the world model of traffic flow. In this model, we have a directed graph G equals to VE and one unit law of traffic, a large population of infinitesimal users that we view as having one unit of volume wanting to travel between two distinguished nodes, V start and V end. For simplicity, we are considering just the single complete version of the model. We assume each HE has a cost given by the latency function LE that is some non-decreasing function of the amount of traffic flowing on HE. In other words, the time to traverse each HE is a function of the amount of congestion on that edge. In particular, even some flow f, where we use Fe to denote the amount of flow on a given He, the cost of some path P is the summation of Le of Fe summing for all those E in P, and the average travel time of all users in the population can be written as the summation of Le of Fe times Fe summing for all those E in E. The flow F is at Nash equilibrium if all flow carrying paths P from V start to V end are minimum latency paths given the flow F. Chapter 18 considers this model in a much more detail, analyzing the relationship between latencies in Nash equilibrium flows and those in globally optimal flows, flows that minimize the total travel time averaged over all users. In this section, we described results showing that if the users in such a setting are adapting their paths from date to date using external regret minimizing algorithms, or even if they just happen to experience low regret regardless of the specific algorithms used, their flow will approach Nash equilibrium. Note that Nash equilibrium is precisely a set of static strategies that are all no regret with respect to each other, so such a result seems natural. However, there are many simple games for which regret minimizing algorithms do not approach Nash equilibrium and can even perform much worse than any Nash equilibrium. Specifically, one can show that if each user has regret little of t, or even if just the average regret averaged over the users is little of t, then flow approaches Nash equilibrium in the sense that a 1 minus epsilon fraction of days t have the property that a 1 minus epsilon fraction of the users that they experience travel time most epsilon larger than best path for that day, where epsilon approaches zero at a rate that depends polynomially on the size of the graph, the regret belts of the algorithms, and the maximum slope of any latency function. Note that this is a somewhat non-standard notion of convergence to equilibrium. Usually, for an epsilon approximate equilibrium, one requires that all participants have at most epsilon incentive to deviate. However, since low regret algorithms are allowed to occasionally take long paths, and in fact, algorithms in the NAB model must occasionally explore paths they have not tried in a long time to avoid regret if the paths have become much better in the meantime. the multiple levels of hedging are actually necessary for a result of this kind. In this section, we present just a special case of this result. Let P denote the set of all simple paths from V start to V end, and let F denote the flow on day T. Let C of F equals to the summations of LE of FE times FE, summing for all those little e in capital E, denote the cost of a flow F. Note that C of F is a weighted average of costs of paths in P, and in fact is equal to the average cost of all users in flow F. Define a flow F to be epsilon Nash if C of F is less than or equal to epsilon plus the minima of the summations of LE of FE, summing for all those E in P, where the minima is taken for all P, the set of paths P. This, the average incentive to deviate over all users is at most E. Let R of T denote the average regret average over all users through E, so RT is as double summation, with outer summation summing for all those T starting from 1 to capital D, and the inner summation summing for all those E in D over the term LE times LE of FE to the T times FE to the T, minus the minimization taken between all paths. For the doubling summation, where the outer summation is summing for all T, the inner summation is summing for all H E in P of the term LE of FE to the T. Finally, let T epsilon denote the number of time steps T needed so that R of T is less than or equals to epsilon times T for all T which is greater than or equals to T epsilon. For example, the RWM and TW algorithms discussed in section 4.3 achieve T epsilon equals to big O of 1 over epsilon squared times log n if we set T equals to epsilon over 2. Then we will show the following. Theorem 4.18. Suppose the latency functions LE are linear. Then for T which is greater than or equals to T epsilon, the average flow F hat equals to 1 over T of times F to the 1 plus F to the 2 and so on plus F to the T is epsilon Nash. Proof from the linearity of latency functions. We have for all LE of FE hat equals to 1 over T times the summations of LE of FE to the T, summing for all those T starting from 1 to capital T. And since LE of FE to the T times FE to the T is a convex function of the flow, this implies that LE of FE hat times FE hat is less than or equals to 1 over T times the summation summing for all T of LE of FE to the T times FE to the T. If we summing over all HE, we have C of F hat is less than or equals to 1 over T times the summation summing for all T of C of F to the T, which is less than or equals to epsilon, plus a minimization taking between all paths, times 1 over E, times doubling summation with outer summation summing for all T, inner summation summing for all H in P of LE of FE to the T. This is by definition of T epsilon, which is equal to epsilon plus the minima chosen between all paths times the summations of the HE in the path P of the term LE of FE to the hat, the bilinearity. So this result shows the time average flow is an approximate equilibrium. This can then be used to prove that most of the F to the T must in fact be approximate Nash. The key idea here is that if the cost of any H were to fluctuate wildly over time, then that would imply that most of the users of that H experience the latency substantially greater than the H's average cost, because more users are using the H when it is congested than when it is not congested, which in turn implies they experience substantial regret. These arguments can then be carried over to the case of general nonlinear latency functions.